All right, hello and good morning, everyone. I hope everyone is having a splendid Tuesday morning. I'm joining you from Pittsburgh, Pennsylvania, on the East Coast of the United States, and I'm really excited today to talk to you all about software supply chain security and some of the challenges that we might have in the current world, or new challenges that have started to emerge. So with that, let's go ahead and jump right in and get started. My name's Seth Vargo, and I am an engineer at Google. I've been at Google just under 5 years now. Before Google, I was an employee at HashiCorp, so you might recognize me from there. And before that, I worked at Chef Software doing configuration management bits. You can find me anywhere on the internet at Seth Vargo. Twitter, LinkedIn, etc. And I'm happy to take questions during the event, but also if you want to ping me on Twitter afterwards, or my direct messages are also open. If you have a question that you don't feel comfortable asking publicly, you can always shoot me a direct message. So with that, let's go ahead and jump in. So what I want to talk about first is how people think they're going to be hacked. And when I say people, I mean like companies or IT professionals or security information officers. People really love to believe that they're going to be hacked or attacked by someone like rapidly smashing keys on a keyboard, breaking through various layers of firewalls and encryptions, just like you might see on television. There's a funny episode of NCIS where there's like two people typing on the keyboard at the same time. And if you know anything about computers, you know like that's not how any of this works. But at the same time, that's how people think they're going to be attacked. And I have this photo, a stock photo I pulled here of, a kind of scary person in a dark room with a laptop. This is what people think, right? This is what they're looking for in terms of an attacker. This is the threat model that most organizations perceive. So think like anonymous instead of random, person just sitting at a coffee shop and hanging out. People also love to think that they're going to be vulnerable to some type of privilege escalation or even better, container escapes. I love hearing about container escapes. Everyone always tells me, oh, but what about a container escape? And I'm not saying that you shouldn't care about these things. Like, container escapes are a real thing, and you should practice defense in depth. And you should think about things like privilege escalation, and you should practice the principle of least privilege. But what you'll find, and my goal kind of here today is to help you understand, is that most attackers are quite lazy. Again, you should care about things like container escapes and privilege escalation, and you should care about the black hat hacker that's sitting in a dark room typing away furiously on a keyboard. But the reality is that you're far less likely to be compromised by someone in those positions or one of those attacks than you are for something much, much simpler. And that's because most attackers are lazy, and we tend to optimize for the path of least resistance. So much like an electrical current is going to take the shortest path between point A and point B, an attacker will often take the shortest path between point A and point B. If your systems are the most secure systems in the world, why would I try to attack your systems when I could instead attack your employees through something like a social engineering attack? Why would I spend hours and hours trying to brute force your password when I could just ask you nicely through a carefully crafted phishing attack and some CSS and JavaScript? So this is how we kind of have to think about security, and particularly like software supply chain security, as we'll see in a bit, because that is becoming the weakest link in this chain. Software supply chain security is becoming the path of least resistance for attackers. And we'll talk about that more in a second. We know that social engineering continues to be one of the most common and easiest ways for attackers to gain unauthorized access to systems. And this is because social engineering exploits the basis of humanity, which is to try to be helpful. Social engineering looks It can look like anything from carrying a bunch of packages so that someone will hold a door open for you so that you can gain unauthorized access to a building, down to creating a sense of urgency or panic, such that people feel obligated to assist on the other end. And it plays into the human condition of wanting to be helpful, of wanting to exhibit, chivalry or helpfulness. And it's very easily exploitable because it's often an unconscious thing that humans do. And really the only way we can help prevent these types of attacks is through education and training. So social engineering isn't a new thing, though. We've been using social engineering attacks. We've been seeing social engineering attacks for almost 10 years now. But there's a new class of attack that's emerging that combines social engineering and software supply chains. And together, this is a rather scary combination. And the pattern looks a little bit like this. But before I show you, I just want to preface this by saying I picked a software package at random. I'm not trying to pick on any one software package or language ecosystem. I really just wanted to show you, with about 5 minutes of preparation, how an attacker might target a software supply chain that you all are probably pretty familiar with. Even if you don't use it yourselves, you've definitely heard of React. Now, I want to be clear that this could happen anywhere. I literally picked the first popular package I could find. And what I'm going to do here is I'm going to look at the dependencies. And I'm going to look at the dependencies of the dependencies. And React actually doesn't have a ton of dependencies, but it does have this transitive dependency called JS tokens. One thing that I really want to point out here is that I did not open a terminal. It's very light in this room. I'm not wearing a hat and sunglasses in the back of a coffee shop. I'm just clicking around in a web browser, right? I'm not running Netcat and making my terminal screen look like an episode of The Matrix. This is all using publicly available information, open source intelligence, and clicking around in a web browser. What I found here is there's a second degree dependency, or a dependency of a dependency, that is incredibly popular that I believe could be a prime target for a social engineering software supply chain attack. It has all of the hallmarks or indicators of a really, really good target. So what does that mean, like a really good target? Well, first of all, it has a critical dependency on a very popular project. So React is very popular. It's one of the most popular front-end frameworks, if you're not familiar. And it's one of the very few dependencies in React. But at the same time, it's of little what I'll call fame. Meaning, when you compare the GitHub stars here, right? React has orders of magnitude more stars, 175,000 versus 272. So we have this very popular thing that's downloaded probably thousands of times every day on developers' local machines that has a dependency on something that most people have never heard of. And that doesn't mean the JS tokens package is not important. It's actually super important, and React couldn't function without it. I'm just saying that you can think of JS tokens as like a syscall in this kind of architecture where the vast majority of people are unaware of it. And if someone went and changed your syscalls under the hood, you probably wouldn't be super aware. And that's what the social engineering software supply chain attacks are taking advantage of, which is like if you saw a massive change in React, you would probably look a little bit further and maybe investigate a little bit. But if you just see a transitive dependency bump to a new version, it's probably important, maybe a security fix, I don't care, and you're going to move on with your life. There's another, so this is kind of the first thing that I would do is like I kind of identified this really, really good target in the ecosystem. So we have popular project, dependency of a dependency that most people have probably never heard of, that doesn't have a ton of attention, not a lot of notoriety or fame. But then it also has another property, which is the second thing that I tend to look for, and the second thing that attackers will look for, which is maintainership or maintainer burden. Again, I want to highlight here, no terminal. I'm literally clicking around GitHub, all open source intelligence, nothing crazy here, no ones and zeros on the matrix screen. And usually what I find is looking at some of these insights, I'll either find that there's one or two maintainers or many, many, many maintainers. So in this case, it's pretty clear that there's really only one maintainer, and I've edited this page a little bit to remove their name and avatar. But you can see here, right, there's two total contributors to this package, and one of them has 3 lines of code and the other one has 10,000 or so. So it's pretty easy to see that this is like a benevolent dictator for life type package. And that means that I can start doing some social research and some social engineering around this maintainer. I can figure out, is this part of their full-time job? If this is not part of their full-time job, if their company does not sponsor this work, if this is a night and weekend project, I can leverage that to my advantage because I can appeal to their burnout, their sense of urgency, the issue backlog, those types of things to try to be helpful. Again, social engineering is all about exploiting the vulnerabilities in humans' desire to be helpful. In the case where there's many maintainers, right? Take a project like React or like Kubernetes, where there's, not only are there maintainers, but there's like committees and subcommittees. You can take a slightly different approach where you get people kind of tripping over their own politics and procedures. And that can help you artificially gain trust. I'll provide an example of that in a second. And then leverage that trust to escalate privilege, not in like the computer science sense, but in the human sense. So let's take a look at what this would hypothetically look like what this attack would look like if I was actually doing this or if I was a consultant doing this. So I would work to earn the trust of this maintainer. So I would probably start by submitting small changes and improvements, fix maybe a typographical error or a spelling error. I would, maybe reorganize the README, gradually start moving into the code, and then I would make some code improvements. Maybe I add a bunch of tests. Everyone loves test coverage. Or maybe I refactor the CI/CD process to move from, one system to another. Or I improve things by making them faster. And over time, I gradually increase the usefulness or effectiveness of my change requests or my pull requests, but I also improve the usefulness of them. So I might start looking at some of the open issues and I see, oh, hey, like this bug's been open for 2 years and it has, 100 plus ones. If I could solve this, I could tell it would be of critical importance to the ecosystem, but at the same time, it would potentially earn the trust and respect of the maintainer. And that's really what I'm going for here, is all of this is in service of earning the trust and respect of the maintainer or the maintainers. So then I'm finally ready to perform my attack. And this largely varies kind of by situation, scale, and what I might be hoping to achieve. The most common approach is to submit malicious code or a malicious change alongside otherwise useful improvements in the same request. So remember, we've already earned the trust and kind of the respect of the maintaining team because we've done maybe 20 or 30 pull requests over many months at this time. So here we decide to exploit people's inherent trust and their lack of time at the same time. So we might go work on a feature that we know is incredibly important to the ecosystem and actually implement it, right? Actually implement that feature and write tests and documentation, etc., but then also inject 5 lines of malicious code. So now what you have is, say, 1,500, 2,000 lines of code that a maintainer needs to review. They're reviewing that from someone they trust, so there's an inherent trust. They're much more likely to just skim that code instead of reading line by line. And you have the pressure of the community forcing the timely review on that maintainer because this is a feature they want, this is a feature they need, this is something they've been looking forward to, we need to get this in the next release, it's very important. And I'm not putting that pressure, which is the reason that it's unlikely to be detected as an attack. The community is putting that pressure in. Hey, we've been trying to get Bitly support for 10 years and this person comes along and adds Bitly support, we need to merge this, it's super important. And you're exploiting that human condition. So that's the first way this attack works is, hey, real feature, real bug fix, real improvement with malicious code somewhere in between, and you hope that it slips through the review process. The second one is a slightly more aggressive form of the first, which takes a lot longer and generally more than one person, but this is where you convince the maintainer that you are trusted enough to be a maintainer yourself. This is often done under the guise of helping the maintainer. Hey, I really really wish that, you didn't have to work so much. If I could take some of the burden off of you. And you can also layer in kind of like some helpful passive-aggressive comments, right? Every once in a while, you might go through and you might be like, oh, hey, maintainer, just to let you know, like, I can't close this because I don't have permission. Or, hey, just to let you know, I can't merge this because I don't have permission. And over time, you're building up this this mentality, or you're helping the maintainer reach their own conclusion that, wow, my life would be a lot easier if I just added Seth as a maintainer. And ideally, you want them to reach that conclusion on their own through a number of subliminal suggestions and hints here and there, because then it doesn't feel like an attack. It's their idea. And it feels like they're rewarding you for something instead of you taking advantage of them. So this is often done under the guise of kind of helping the maintainer. The third attack occurs whenever you have many, many, many maintainers. So again, think like very large project with special interest groups and subcommittees. And here what you do is you leverage the fact that most of the people on those subcommittees either don't know one another or don't talk on a regular basis as a method to exploit the human condition. So you may submit a pull request. Maybe you know that there's someone named Sherry on some special interest group. You wait until you know that Sherry is asleep. You then go into the community Slack channel, you mention another maintainer, and you say, hey Chris, I was working with Sherry on this pull request. Sherry said that it would be merged, but it wasn't merged. It really needs to go out. Can you just approve it here? And this is exploiting the fact that you're leveraging or you're borrowing Sherry's trust here. Even though Sherry never actually trusted you, you're leveraging the fact that Chris probably knows who Sherry is, or at least heard of Sherry, recognizes that Sherry is a member of some interest group or some steering committee, and then you're borrowing Sherry's credibility for your own nefarious use case. This only works when there's a lot of maintainers that aren't super familiar with one another. So it doesn't work if all the maintainers work at the same company, or it doesn't work if the maintainers do actually know one another. But in really large projects or projects that have a lot of governance structure, it's pretty easy to exploit some of these human factors. Which brings us to the fact that this is not a new thing. And I actually just saw a question come in the chat about the University of Minnesota, which we will talk about in 3 bullet points. So these are not new attacks, right? So event stream, there was an attack also in the Node.js ecosystem in 2018 on the flat map stream, which was imported by hundreds of thousands of packages. This is actually nearly identical to the hypothetical attack I described earlier on JS tokens. Again, transitive dependency of a dependency that many, 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 many things depend on that most people have never heard of, and an attacker was able to get malicious code in, again, through compromising the trust of a maintainer and exploiting that human condition. I'm sure folks are familiar with SolarWinds. This is an attack largely stemming from a backdoor, so a little bit more on the code side, a little bit less on the social engineering side. But it affected many, many, many customers, including some really big brand name customers. There was a Mimecast last year involving a compromised cert, a CA cert. Dependency confusion, which is one of my favorite attacks because it really speaks to that path of least resistance that an attacker will take. The attack here, if you're not familiar with it, I'll just give you a quick summary, is many package ecosystems like Ruby Gems, NPM, Python had vulnerabilities such that when given multiple sources for which to resolve packages, they would always prefer the publicly available registry over a private registry. So for example, companies like yourselves or like Microsoft, Apple, Uber, and Tesla, they might run something like an Artifactory or a Ruby Gems mirror or an NPM private instance where they put their own private packages. And they reference those in the same package lock or gem file. And what researchers found, thankfully these were white hat security researchers, was that if they could guess the name of an internal package, so maybe they knew the code name of a project or just did, frankly, some trial and error, if they could guess the name of an internal package that existed on the internal instance of one of these companies, they could publish that same package with the same name to the public registry, and the build process would automatically pick it up and inject it into the code. So this was a zero touch, no social engineering on the company side of things to inject code directly into someone's build process, which is pretty scary if you think about it. I still consider this a form of social engineering because you may have to talk to employees or do some open source intelligence to figure out like what might these package names be, what's the naming format. You may even need to leverage some employees or some ex-employees or disgruntled ex-employees to get that information. But once you have it, this is a completely hands-off attack. All you did was push a package to a public registry. Most of these have been fixed now, right? But these are the types of attacks where, again, people like to think you're going to be attacked by some black hat hacker sitting in a coffee shop with dark sunglasses and a baseball cap. But in reality, these attacks are simultaneously more sophisticated, but also much simpler than you might think. And then we obviously have the Linux hypocrite commits, which were from the University of Minnesota, which were the failed attempts to intentionally introduce vulnerabilities into the Linux kernel. Not only did that get the University of Minnesota banned entirely from contributing to the Linux kernel, but it was largely unsuccessful. And we can actually learn something from this because the reason it was largely unsuccessful was because the Linux community and the Linux maintainer group in particular has both a benevolent dictator for life, right? You have Linus, and they know one another. And that's why they were able to quickly identify and revert these commits. When you don't have those properties in a software system or in a software supply chain, it's very reasonable for these things to live for a very long time. So my point here is that this isn't new. Supply chain attacks have existed since the 1600s, right? Like pirates are supply chain attacks. Software supply chain attacks have existed really since the late 90s, early 2000s. So this isn't a new problem. The question is like, what can we do about it as either software engineers or security engineers or practitioners? Well, if we think about the flow of code from a developer's local machine into what I'll call production, and I'm using air quotes here in production because I don't necessarily mean that this is going to like a web service or an on-premise like binary. This could be a package, right? This could be publishing something to NPM. It could be publishing something to Ruby Gems. But it could also be some end web service. It looks a little bit like this, right? So I have a developer, I have my local machine, and I'm going to push my change into source control or some source control management system. Ideally, there's some build process, either automated or I have to kick something off, a Jenkins, a Travis, a Circle CI, a GitHub Actions. That's going to build and maybe run my tests, maybe do some CI/CD. Then there's a packaging step. So this might be, compiling a binary. This might be, doing like npm package, whatever it might be. And then there's the push phase, which is getting into production, which again could be like deploying to Kubernetes or it could be pushing to a registry. If it's pushing to a registry, that distribution then could become a dependency of some other build process. Right, so I may build my little library that does tokenization. I might push it to my internal package registry, and then my next build for some other software piece picks that dependency up. So again, this is a pretty common flow. It's very generalized for how code may get from a developer's local machine into air quotes production. The problem is that every single one of these arrows is actually a vulnerable point in the software supply chain. A developer can submit bad code, right? This is an internal threat, but if I'm a malicious employee, I can submit bad code into the source control system, especially if I don't require peer reviews or approvals. As an attacker, I could compromise your source control system. So can I gain unauthorized access to your code? If I can do that, through the maintainer attack that we talked about, I could modify the code, I could change the code, I could alter the behavior of the code, potentially way, way back in history where you would never see it. If you don't have a secure connection between your source pipeline and your build pipeline, a processor and attacker may be able to modify the code there. So if your CI/CD system is pulling code from a non-TLS URL, for example, I may be able to compromise that endpoint and maybe perform a minim attack and get your CI/CD system to pull in the wrong code. If you don't have a secure build platform, right? If your build platform is exploitable, if I can get access to, say, the raw VMs or the raw Jenkins executors, I could compromise that. If I can just bypass the entire CI/CD process entirely, right? If as a local developer, if I have credentials to just push directly to NPM or push directly to Ruby gems, I could bypass all of this anyway, even if all these checks are perfect and you can't compromise the build platform. A little bit harder, but I could try to compromise the registry. We've seen attacks where folks have tried to like squat on a particular package name or overtake a package name in an attempt to perform a malicious injection attack. And then if I can convince your production runtime to use the wrong package, even if you followed all this stuff, if I can, typo squat or something like that, and I can convince you to use the wrong package or use the wrong dependency or use a bad dependency, I can compromise the software supply chain. So again, this begs the question, like, what can we do about it? We have to be realistic. We can't, like, Thanos snap our fingers and magically make everything secure. This is going to be a journey, and the first step in this journey is awareness. And then the second step is we need a common framework and a common language for which we discuss the security, particularly the software supply chain security of a particular software system, build, artifact, or distribution. And that's actually one of the things we've been working on at Google. So we have a program called SALSA, just like chips and salsa, which stands for Supply Chain Levels for Software Artifacts. And this is actually based off of an internal secure code development and distribution process we've had at Google for a very long time. We call it BSID. But SALSA is the open source externalization of this framework. And there's 4 levels. There's what we call SALSA Basic, which is basically just kind of the bare bones minimum. There's technically SALSA 0, but we don't talk about that one. It's no protection. There's SALSA Medium, which is against origin protection. SALSA Advanced, which is really about some of the other specific arrows in the previous diagram. And then there's SALSA Maximum, which has the maximum reliability of the software supply chain in terms of auditability and checking. And SALSA kind of has this progressive incremental framework. So like I said, we don't talk about SALSA 0. SALSA 0 means like nothing. Everything is, I call SALSA 0 YOLO mode. But SALSA 1 has 2 pretty strict requirements, but they're pretty easy to attain. We need a scripted build, and we need some type of provenance of the dependencies. That could be like a package lock.json with a hash to make sure it's unmodified. And then the scripted build is just like, it could be a shell script, or it could be something as rigorous as like a full CI/CD process. SALSA 2 introduces version control, an actual build system, and then really starts hammering down on the like provenance side of things. So that provenance needs to be authenticated. It needs to be generated by a service, meaning a human can't be manually compiling these manifests. And then as we get into SALSA level 4, we're talking about things like indefinite retention of binaries for both current and retrospective analysis, 2-person reviewing any code change that goes into the system, making sure that the builds are parameterless, making sure that they're hermetic, and making sure they're reproducible where possible, and then also making sure that you can't falsify or funge things like provenance, and making sure that you have the complete list of dependencies, including things like alt test dependencies. So SALSA level 0 represents basically no controls, while SALSA level 4 represents the highest degrees of confidence that software has not been tampered with. And each one of these rows in this chart here actually corresponds to one of the red arrows in the diagram I put together before. So SALSA is still in like the super, super early phases. It's a framework, so there's not a whole lot of like, go download this thing and run it. We do have a GitHub action and an Azure DevOps integration for creating the provenance today. So if I go back to the previous slide real fast, you can see that provenance is the third part of this table. And there is a GitHub action and Azure DevOps integration for automatically creating that provenance and checking it into your repository during a build step. So again, we're working on this. We're super interested in community feedback. We're super interested in how the community perceives this. But the idea is that it's a way that we can commonly talk about and express dependencies. So when someone says, hey, this package is SALSA level 1, we know exactly what that means. But the best part about SALSA is that it's non-transitive. So, and you can read more about this in salsa.dev, but what this means is that even if you have a dependency that is salsa level 0, meaning no checks, no balances, nothing, you can still achieve salsa level 4 in your code, even though you have a dependency on a salsa level 0, just by taking a few additional steps, like producing, an artifact manifest for that salsa level 0 dependency for your code. So this is really beneficial because it actually doesn't require us to secure every single dependency in every single package ecosystem. It allows us to make small incremental process, because that's ultimately the only way this will be successful. We can't, again, just snap our fingers and expect things to magically be secure. So that's all I have for you all today. Thank you all so much for joining. Again, my name's Seth. You can find me at Seth Vargo anywhere on the internet. And again, if you don't feel good tweeting at me publicly, you can always direct message me. My direct messages on Twitter are open. A few quick links. So you can learn more about Salsa at salsa.dev or github.com/salsa-framework/salsa. And I've also included a link to the Google white paper that discusses the internal processes, which I call BCID, that Google's been following since about 2013, that Salsa is kind of based on. It's like the externalization of that. Thank you all so much for having me, and I'd love to take any questions in the time remaining.
We have one question. What do you think about the University of Minnesota introducing bug in the kernel? Rising awareness or playing with the fire? What is your opinion about that?
Yeah, thanks. Thank you for the question, Dan. I think it's both. Like personally, as someone who works in this industry, you should never attack a target without the consent of that target. So that was not in line with any like code or ethos. Had the University of Minnesota worked with the Linux maintainers or a subset of them and said, hey, we want to carry out this research, this is how we'd like to do it, and getting the approval of a subset of the maintainers, that would have been more ethical. At the same time, it certainly got like front page press, and it started to get people thinking, especially after SolarWinds had just happened a few months earlier, really thinking about the software supply chain. So I do not believe the University of Minnesota's original intention was to raise awareness around software supply chain security, but I do believe that an unintended benefit, particularly because of the news and the press cycle around the actions they took, did bring a lot of awareness and frankly some concern. It helped people understand the severity of some of these things. But I believe they're still banned. The whole university is still banned from contributing to the kernel.
Thank you for your answer. And we can wait for a few maybe minutes if we get some other questions. And what have you been doing yesterday when the Facebook go down?
Tweeting about DNS. No, I have a Facebook account. I honestly don't use Facebook that much, at least not nearly as much as I did in college. We do use Facebook Messenger a lot to keep in contact with a lot of our friends. And I know a lot of like my relatives and stuff were pretty upset that WhatsApp was down because they use that to communicate, particularly internationally. So that was not super great for folks that needed to leverage those technology stacks for communication or in some cases emergencies. But I'm glad they got it fixed. I read a little bit of the postmortem this morning. As always, it was a configuration change. All major outages are configuration changes. So I'll be interested to learn a little bit more about as they dive deeper into some of the chain of events and where some of their controls and processes broke down.